if I have a boundary between two materials and I have a wave that encounters that boundary at a certain angle as measured from, what do we call that dotted line? That dotted line is what we call a normal line. In physics, normal means 90 degrees. In physics 20, we talked about the normal force, 90 degrees to the surface, right? This is a normal line, 90 degrees to the boundary between two different materials. If this ray of light strikes that boundary at a certain angle as measured from the normal line right here, and then it bends when it goes into the new medium, such that the angle as measured from the normal line either decreases, as it is in this case, or increases, what do we call that? What phenomenon is that? That's called refraction. Refraction is the bending of a wave when it goes from one medium to another. Do you remember what causes refraction? Fundamentally, when we go from one medium to the other, this changes. And as a result of this changing, there's a couple other things that change as well, including the direction. It's the speed, yeah. So when it goes from one medium to another, the speed changes. It either slows down or speeds up. And that results in the angle changing as well, the direction changing as well. What else changes as a result of the speed changing? The wavelength. What doesn't change ever once the wave has been made? Amanda? Good, the frequency. So V changes, lambda changes, theta changes, but the frequency doesn't change. The frequency remains the same. Now, each of these media is just the plural for medium, so each of these media has what we call an index of refraction, N. We'll call this one N2, because that's the medium it's going to. We'll call this one N1, because that's the medium it's coming from. What was index of refraction? What was the definition for that? There was a kind of an everyday understanding definition, and then there was a real sciencey definition. You give me either one, and I'm happy. Yep. Yeah, that's kind of the way that we understand the index of refraction, right? It's the amount that light bends in the medium. Now, the amount of bending is dependent upon the speed, right? That's what we said before, right? As speed changes, then that causes a change in direction. So the amount of bending is dependent upon the speed. If we think of index of refraction as the amount that light bends, then the real definition is going to relate to speed. Specifically, it's going to be the ratio of the speed of light in a vacuum to the speed of light in a certain medium. So the index of refraction of medium 1 would be C over V1, or the index of refraction up here would be C over V2. Now, what do we know about V2 and V1, not relative to each other, but relative to C? V1 will always be slower or the same, right? V1 would be less than or equal to 3 times 10 to the 8 meters per second. Same with V2. V2 will always be less than or equal to 3 times 10 to the 8. Usually less than, occasionally equal to. That means that N will always be what? N will always be greater than or equal to 1. Greater than or equal to 1. Right? You always have to have a number that's at least 1, because the number on the top is either the same as the number on the bottom or bigger than the number on the bottom. Same deal up here. N2 will always be greater than or equal to 1. Make sense? Now, every material we said has its own unique index of refraction. Truly, every material has multiple indices of refraction. What affects the index of refraction for a particular material? Who was it? I can't remember who it was over here that said the frequency doesn't change. Was it Amanda? Okay, Amanda said the frequency of a wave, once a wave has been made, never changes. But the frequency can cause a change in the index of refraction, and it does. If you have red light going through glass, it will bend a slightly different amount than blue light going through glass, and that's because red light, or glass, for red light, has a slightly smaller index of refraction than glass does for blue light. So we have different indices of refraction for different frequencies, for different colors. And that results in a phenomenon called dispersion. The Pink Floyd phenomenon, The Dark Side of the Moon, my 137th favorite band of all time. when white light, or we'll draw it as yellow, encounters that boundary between air and glass, and that white light that consists of all the colors bends, each different color will bend a different amount because that glass has a slightly different index of refraction for each different color, each different frequency. Tell me, which one bends the most, which one bends the least? I got a red pen in my hand. Is it going to bend the least or the most? It's the least. In other words, the index of refraction for this glass for red is slightly less than the index of refraction of this glass for blue and for violet. So we end up getting something like this. Over here on the right-hand side, we get what we call a spectrum. Specifically, we call it a continuous spectrum because unlike on the Pink Floyd album cover, we don't see a distinct red band and then a distinct orange band and then a distinct yellow and so on. We see red kind of transitioning into orange, which transitions into yellow. There's no defined borders between them like there is in the picture up on the wall over there. Does that make sense? Continuous spectrum because it continually changes from one frequency to another. Right? So I got to ask you the question, higher frequencies produce blank index of refraction. What's the answer? Lower or higher? Higher frequencies produce higher indices of refraction. Blue is the higher frequency here, right? It bends more. Therefore, this glass must have a higher index of refraction because it causes light to bend more. What if I said higher wavelengths produce blank index of refraction? Higher wavelengths are the same as lower frequencies. And lower frequencies, we think back to the diagram, we look at the diagram here, we can see that lower frequencies produce a smaller index of refraction. And we know that because the light bends less. Does that make sense? All right, that's dispersion. Next, we took a look at we'll take a look at a law that we call Snell's Law, which provides for us a relationship between some of these variables that we say change when we go from one medium to another. Now, when we use Snell's Law, we're going to assume the index of refraction for a particular material is constant. That's not quite true. It's unique for each unique frequency, but it's close enough that in most cases we can say that glass, for instance, quartz glass that is, has an index of refraction of 1.47. Although it could be a little higher, it could be a little lower, depending upon the frequency of EMR that you're actually using. But on average, we'll say 1.47, that's the value that we'll end up using. You can see the expression or the equation that gives us, that is Snell's Law on the board right now. You can see that there's 8 variables in there. Sine theta 1 over sine theta 2 equals V1 over V2 equals lambda 1 over lambda 2 equals N2 over N1. Let's move that and redraw this diagram here. If the ray of light is going from this medium to this medium, then we're going to call this one medium 1 and this one medium 2. This would be theta 1, the angle as measured from the normal line. This would be theta 2, the angle as measured from the normal line in the second medium. V1 would be the speed of the light down here, and V2 would be the speed of the light up here. Lambda 1 would be the wavelength of the EMR down here, and lambda 2 would be the wavelength of the EMR up there. And finally, N1 would be the index of refraction down here, and N2 would be the index of refraction up here. Now, listen carefully to what I'm about to say. We can see that in this diagram, theta decreases, right? Theta 2 is smaller than theta 1. Would you agree with that? Theta has decreased. What do you think is going to happen to V? Is V going to go up or down based on the equation that you see up on the board right now? Yes. If theta is decreasing, V is decreasing as well. What about lambda? If theta decreases, what happens to lambda? It's decreasing as well. If theta decreases and V decreases and lambda decreases, then N is going to increase. That's right. So usually you see a problem where you're given the indices of refraction and you have to determine A, what the diagram looks like, okay, which way the ray bends, whether it bends such that theta 2 is smaller than theta 1 or bigger than theta 1, and you have to determine oftentimes what V2 is or what the lambda 2 is or whatever the case may be. You know that if N increases, all the other variables decrease, and if N decreases, then all the other variables will increase. Right? Make sense? N is inversely related to all of those variables. Now, in a moment, we're going to solve a couple of problems, a couple of example problems. In those example problems, or at least in one of those example problems, you're going to find that you need to use Snell's law. And Snell's law has 4 parts. Sine theta 1 over sine theta 2, V1 over V2, lambda 1 over lambda 2, and N2 over N1. You guys know from everything that you've done for the last 13 years of school, you're only going to use 2 parts of an equation. Right? Pick the 2 parts that make the most sense. Like look at what you're given, draw a picture, look at what you're given, and then use those 2 parts. You can say sine theta 1 over sine theta 2 equals V1 over V2. You can also say V1 over V2 equals N2 over N1. Whatever it is that fits the givens. This isn't meant to be a complicated equation because it has 4 parts. It's meant to be a versatile equation because it has 4 parts. All right? Okay. The first example says calculate the speed of light in Ruby. Now, you can see on your paper that I handed out to you, there's a little table of various indices of refraction. You can see on that table that a vacuum and air has an index of refraction of 1.00. That just means the ratio of the speed of light in a vacuum to that medium is 1, which makes sense, right? Since light travels at 3 times 10 to the 8 in a vacuum and at 3 times 10 to the 8 in air, 3 divided by 3 is 1. But then you go up from there, which means that as you go into ice, light bends. As you go into glass, light bends more. As you go into ruby, diamond, light bends even more because the ratio of the speed of light in the vacuum to those mediums or those media are higher. Our question here, using the table that's in the top right-hand corner of that of your example problem sheet, says calculate the speed of light in a ruby. Now the easiest way to deal with this is simply to use the definition for index of refraction, which, by the way, is not on your data sheet, even though it really looks like an equation. We say N is equal to C over V. It's not on your data sheet because it's really just a definition. No, it's an equation, obviously, but it comes straight from the definition, the ratio of the speed of light in a vacuum to the speed of light in air. So we have to remember this, or we have to just derive it from the definition. We're going to rearrange this to solve for V, the speed of light in Ruby, which ends up being C over N, the index of refraction for Ruby. So it's 3.00 times 10 to the 8 meters per second, divided by the index of refraction for Ruby, and you can see on your sheet that that is 1.54. We'll say 3.00 times 10 to the 8 divided by 1.4 gives me 1.95 times 10 to the 8 meters per second. Remember what we said a little while ago? We always expect V to be smaller than C, smaller than or equal to C. Is it smaller than here or equal to? Yeah, it's quite a bit smaller, right? It's smaller by a factor of about 1.5, right? 50% smaller. Hence the index of refraction, it's 1.54. Second example, and this is where we'll leave it for now, before we get you working on some questions. It says light passes from water to ice at an angle of 40 degrees. This isn't worded well. Okay, let me caution you on this. It's not worded well. Typically, and you'll see in the problems that you're working on in a few minutes, typically it's worded better than this. What I mean by this is that it passes into the ice. If this is water and this is ice, it passes into the ice at 40 degrees here. In other words, that's theta 2. Does that make sense? And we can figure that out by the wording of the question, but it's still not worded well. We want to determine the angle at which the light struck the water-ice boundary. Now, in other words, we want to find theta 1. Now, what's the index of refraction for ice? 1.31? That's going to be N2, because we're going from water to ice. We're going to medium 2. N1, which is water, we're going to say N1 is 1.33 from that same data sheet. So index of refraction is decreasing here. Not very much, just slightly. What would you expect to happen to V, the speed of the wave, as it went from medium 1 to medium 2, when the index of refraction is decreasing slightly, Kessler? You would expect it to increase slightly, right? The speed will increase slightly. If the speed increases, the wavelength will increase. If the speed and wavelength increase, the angle will increase. So we would expect the diagram to look something like this. Theta 1, don't know what it is, but it's smaller than theta 2. Does that make sense? We want to always, for these Snell's Law problems, draw the diagram. It makes it a lot easier to plug your numbers into your equation. And we want to, as much as possible, draw them accurately so that we have theta 1 bigger or smaller as appropriate than theta 2. And we've done that here. Okay, let's say sine theta 1 over sine theta 2, since we're looking for theta 1 here, equals, let's use N2 over N1. So sine theta 1 over sine 40 degrees is equal to N2, the second medium, which is 1.31, over 1.33. Okay, let's figure that out on our calculator here. Let's say 1.31 divided by 1.33 gives me 0.98. Let's multiply that by sine 40, 0.633. And then let's take the inverse sine of that, and we get 39.3. What did we predict? We predicted theta would go up. Did it go up? Yeah, we went from, yeah, it did. Theta 1 was 39, theta 2 was 40, right? We predicted it would go up, but not by much. And it didn't go up by much. Why didn't it go up by much? Because N1 and N2 are almost the same. If they're almost the same, you're not going to get very much bending at all. Therefore, the direction is going to be almost the same. All right? All right, we're going to give you a little bit of time here to work on some questions on worksheet number 17. And those questions that I want you to work on are, for now, questions 1 to 8. There are more questions. Please don't try going beyond number 8. You don't know how to do those yet.